Thank you very much, Chris. It's great to be here. Thank you for coming. I want to actually start by just talking a little bit about Anna. Anna came to me through a mutual colleague in Alaska because she was interested in getting a grant to go to Antarctica with the Artists and Writers program that the National Science Foundation funds. And most artists and writers that go to Antarctica want to go to the National Geographic Antarctica, meaning penguins and seals and killer whales and stuff. And Anna wanted to go up on the ice sheet where it's flat and white and boring. And I remember thinking when she came to talk to me, okay, lady, if you want to come into our lab and paint white stuff, go for it. You know, I don't know about this. And it's funny because over the years, other colleagues that have known Anna have sort of joked about the same thing, like, why doesn't she just submit a bunch of white pieces of paper? I mean, that's all that's out there. And this was very naive of us, because of course we scientists that work on ice should have known better. We love this stuff. It's beautiful. And Anna somehow figured this out in spite of our skepticism. And as I think you'll see when you see her work, she's done a fabulous job of proving us wrong. But my real goal now is to just talk a little bit about the science that I do, that we do in Antarctica and Greenland in particular, and to try to give you some feel for what kind of discoveries are made and why they're important, but also to talk about the beauty of it all. A lot of the work that I do gets interpreted by people that talk to me about it in the context of global warming. It's extremely difficult to talk to, say, a New York Times reporter who's heard that I've published a new paper in a leading journal, and they call me up and they say, so what does this have to do with global warming? And over the years, I've learned that when it doesn't have anything to do with what they want it to be about, to say, it's totally irrelevant. Do you still want to talk to me? And they usually hang up at that point. Not all of this is about climate change in the future. Some of it is just about understanding how the system works. And I'm mostly going to talk about that now. But back to the beauty of it. This is a photo I took on the Antarctic Peninsula, the bit of Antarctica that sticks up towards South America. And this is the sort of National Geographic Antarctica. There are seals swimming around in this bay, which we saw. No penguins on this particular trip, but this is sea ice, which has been floating around in this bay, and it's summer, and it's melted, and it's drifted onto shore. But up on the summit here of this mountain, this is actually really tall. It's about 10,000 feet above me. It doesn't look like that. It's big. It's far away. Colleagues of mine from the British Antarctic Survey drilled an ice core up there. And what I do, what most of my work is involved, is drilling into this ice to get at ancient ice, snow that fell tens or hundreds or thousands of years ago, and to extract information from it about how our climate and how the ice itself has changed through time. We are, of course, interested in what's happening now, and one of the things that's happening now is that the great ice sheets, Greenland and Antarctica, everything you see in color here is ice. And what's shown is a color map based on satellite data of the rate of thinning or thickening of that ice. If it's blue, it's thickening. If it's red, it's thinning. And the basic picture is that the margins of the ice sheets are thinning and contributing to sea level rise. And that's important and interesting. This is a photo taken, I think this actually may be a satellite photo, of one of the camps that Anna visited at the central part of West Antarctica. I should back up. We're right about here in Antarctica. South America's over there. Australia's over that way. Well, actually, over this way. New Zealand, Africa. That camp is located right here, and you can see basically featureless terrain with some snow dunes, like sand dunes, but they're sastrugi, they're called. And the drift pattern that is created from all of the boxes that we leave there over the winter. Pardon me? And what we're going to do is below that surface is 3,000 meters, a couple of miles of ice. And the snow that falls here doesn't melt, it just gets buried by new snow, and so it travels downwards into the wall there, and we can go and drill it and get ancient snow. So here's a picture from the surface a couple meters down. And a wonderful thing to do in these settings is to dig 2 pits like this and cover one of them up so the sun doesn't get in. And there's one next to it, and there's about a foot of snow in between, and the sunlight comes through, and you get this beautiful cathedral-like impression. The truth is, we do this all the time because it's beautiful, not because we're doing so much science in there. But there is science to be done. We sample the snow, and the person's thumb here is located at the base of the most recent summer snow layer, and this is the previous winter and the previous summer. And they're a little bit like tree rings. You can kind of count down the layers. But this is just a couple of meters. There's thousands of meters of snow below this person, and it's all being compressed, so it's turning into solid ice. To extract an ice core from a place like that that's so deep, you wind up using a fair amount of technology. It's fairly simple technology and concept, but there's a lot actually that goes into it. The ice is flowing, and you have to deal with the fact that, well, you don't want the drill to get stuck. It's about $1 million piece of equipment. So a large infrastructure was created. This is called the arch. A large pit was dug to allow this rotating apparatus to put the drill into the ground. Here's the core barrel itself. And what comes out of this is a beautiful object. This is about 2,600 meters below the surface at the West Antarctic Ice Sheet divide, the center of the West Antarctic Ice Sheet. And for the most part, the ice is absolutely crystal clear. It's the most beautiful, sort of pure, clear ice. There's no bubbles visible in it if it's very deep, because there's air in the ice, but it's been compressed out by the great pressure. In this particular picture, though, there's a dust layer from a local volcano that erupted 20,000 years ago, or whatever age that is, I can't remember. And you can see this as a nice layer in the ice. And we can use the geochemistry of these layers actually to get dates to figure out what the precise age of the ice is. And then we bring all this ice back to the National Ice Core Laboratory in Denver, actually in Lakewood, west of Denver in Colorado. And it's minus 40 degrees in here, and there's something like 20 kilometers, 15 miles or so of ice from various parts of the world, the polar regions and also alpine glaciers around the world, stored there. And then this beautiful ice that we've worked so hard to get out of Antarctica and keep frozen, we then destroy. You can see here in this beaker little bubbles that are appearing in this ice which contain ancient air. I don't know how old this particular piece is, but the oldest ice that's been retrieved from Antarctica is over 800,000 years old. And from these measurements, from these collections of samples, we have a record of a lot of different things in the atmosphere, including the carbon dioxide level, going back that far, almost 1 million years. So I could talk forever about the various important discoveries that have been made through this research, but I want to talk in particular about what I think is probably the most surprising discovery that was made in the early 90s by researchers working in Greenland. This is data from an ice core in central Greenland. The x-axis shows the age before present in thousands of years. So this is 60,000 years ago. This is essentially today. And on the y-axis is something called the oxygen isotope ratio. And I'm not going to tell you anything about it now. I'm happy to answer questions later. But in essence, this is a measure of past temperature. And what you're seeing is it's warm today. It's been warm for about 10,000 years. This is the so-called Holocene period. Most of human evolution, as we think of it at least, has happened in this time period. And all of civilization has happened in this time period. Before the Holocene in Greenland, well, we've known for a very long time there was an ice age 20,000 years ago. Seattle was covered in a couple miles of ice, for example. Bellingham was covered in even more ice. We knew it was colder, and that's what this shows, but it also shows that there were very rapid fluctuations in temperature that occurred through time. And prior to the early 90s, when this ice core was drilled, we only had a vague notion that this had happened, and we really had no idea how quickly it had happened. And in fact, a colleague of mine at the University of Washington, a very famous atmospheric scientist, in the previous version of his textbook, there's actually a sentence that essentially says, this cannot happen. And here's all the physics explaining why this can't happen. And then this ice core came along and said, you got to rewrite your book. So I'm going to now blow up this graph. into this little section of this record from about 10 to 20,000 years ago, 12 to 15 actually. And this is the same measurement. This is a rapid warming event, and this is a rapid cooling event. And there's a bunch of these kinds of things, but this is a particularly dramatic one. This is about 15 degrees Fahrenheit of warming at the summit of the Greenland ice sheet in about 50 years. So just think for a minute about what it would be like to live in Bellingham, and next year it's a degree warmer on average than this year, and it keeps going like that for 20 years or so. And then suddenly it's just always 15 degrees warmer. That's, if you're the owner of the Baker ski area, where it's typically just around the freezing point, this is bad news, right? This is a major, major climate change. Now, when this work was originally done, it was thought that perhaps this was a global change in temperature. It turns out that this is a fairly localized change. There weren't changes that large anywhere, except the high latitudes of the northern hemisphere. But the impacts of these events were felt everywhere. So this wasn't a global warming thing. It actually cooled in some places and warmed in others, which is a really important distinction from what is happening now. This is a record from Antarctica that we just finished last year, essentially. Same time scale, 60,000 years, oxygen isotope ratio, essentially temperature again. And again, it's warm today, and it was colder sometime in the past, and there are these fluctuations through time. But the really interesting thing is when you put these together, they're not the same, they're different. The amplitude of the Greenland changes is larger, they're faster, and the amplitude of the Antarctic changes, well, I already said this, they're smaller, but also they seem to be slower. And if you look at this in some detail, just as an example, this one, it's sort of clear. Antarctica seems to be warming up for a while, and Greenland's sort of sitting there fluctuating, but it's not doing this rapid warming, and then suddenly it warms up. And almost all of these events are synchronous in that the rapid warming occurs right at the top of the Antarctic warming, and then they both cool together. And this has been vaguely known for probably 15 years now, but working out why this has just been an interesting scientific discovery, a scientific journey for the scientific community. Why does it work this way? The answer that we think is correct, that just a few years ago I thought was wrong, but I'm increasingly of the opinion it's right, is that what's happening is large changes in the ocean circulation. The ocean and the atmosphere transfer heat from the equator towards the poles, but they also transfer heat between the two hemispheres, the southern and northern hemisphere. And this little movie is just showing from a computer simulation a big sophisticated supercomputer climate model going from 18,000 years ago to 12,000 years ago, roughly the same time period that I was just showing you in that blow up. The red is the Greenland simulation, and the blue is the Antarctic simulation. These are the estimates of temperature in those two locations from the model. And what's shown here let me actually start this over. What's shown here are the change in the temperatures of the ocean, going from north, this is 80 degrees north to 80 degrees south. In the Atlantic Ocean, this is the depth of the ocean. And the colors are how much different from average the temperature is. And this is another measure, essentially, of the ocean current flow that I won't talk about in detail. But what happens at this abrupt warming event in Greenland is a sudden change in the ocean circulation, which transfers heat, changes how much heat is transferred between the hemispheres. And you can see there's this very interesting and sort of complex pattern of colder and warmer and warmer and colder and warmer that occurs through time. And the fidelity of this model and the data is remarkably good, actually. Again, I wasn't convinced of this just a few years ago, but as we've done more and more work, as better computer models have been produced, the degree to which the theory as encapsulated in the computer model, which is just put physics of ocean circulation, and the results that we actually observe on the planet, I think is compelling. So what this tells us is that the system has this interesting complexity. It can naturally do all kinds of complex things. Temperatures can change quite dramatically in certain parts of the planet and change in another way in another part of the planet. Again, none of this was known 20 years ago. It's a new discovery, and it's a new understanding about how the system works. So That's sort of esoteric. It's interesting. Why does it matter? Well, I already showed you in a different way that the margins of the ice sheets are changing. And this, again, is showing the rate of thinning of the Antarctic ice sheet. And the greatest thinning is occurring in this part of Antarctica, quite close well, it's 500 kilometers away, but it's the same part of Antarctica where this ice core was drilled. And the red is showing the places where the thinning is happening the fastest and where the greatest amount of ice is going into the sea and contributing to sea level rise. This is Pine Island Glacier. This front of ice here, as viewed from a ship, is about 100 meters tall, maybe 200 meters tall. But this is a floating glacier. There's 90% of it's below the water. So this is a large amount of ice. It's a kilometer or two thick. And this thing is collapsing. It's breaking up. It's falling into the ocean. And really just in the last few years, it's become clear why. It's not just, quote, global warming. It actually has nothing to do with warmer air temperatures. It has to do with warmer ocean temperatures. This is a map of Antarctica, again, showing now in detail the rate of thinning of the floating ice shelves that come off the continent and into the sea where they collapse. And shown around in color is the mean ocean temperature, just sort of schematically. Basically, it's warm water over here. And that warm water is getting under the edge of the ice shelf, under the edge of the ice sheet, and causing it to melt at a very rapid rate. The units here, the brightest red is 7 meters per year of melt. Very, very fast. This then is a blow-up of this area, the Pine Island Glacier area, and it's showing, it's just a topographic map, essentially. It's showing where it's deep, out in the deep ocean here, over 1,000 meters, and the yellow is the continental shelf. And what is and Pine Island Glacier is over here. This is this area that's thinning very rapidly. And what's happening is that warm water, even though it's Antarctica, the air temperature might be minus 40, the water is relatively warm. It's 2 degrees Celsius. And that stuff laps up onto the continental shelf and gets up against the edge of the ice, and it's much warmer than the ice, and it melts the ice. Our record of observations about the climate in Antarctica is from direct measurements, from instruments, from temperature records. It's very, very short. This shows from 1800 to 2000 the temperature data we have for West Antarctica. There's actually only one weather station with any significant amount of data there in the center of the ice sheet, near where we drilled the ice core. And if we just had this information, we would say, oh, it's been warming up for the last 50 years. The ice core record, which goes back thousands of years, and I'm just showing the top 200 years, shows that, yeah, that mimics the temperature record. It's going up, but there's all these fluctuations on top of that. And it turns out that every single one of these large warming events is actually an El Nino event. How many people don't know what El Nino is at all? Have you heard that term? Okay, so the tropical Pacific warms up during El Nino years. You have increased rainfall in California. You usually have lousy skiing in Seattle. You also have climate changes in Antarctica. And here's a nice little movie showing how the tropical Pacific and Antarctica, and for that matter, California and Washington are related to each other. This is a computer model simulation of, I keep walking away from the mic, of the atmospheric circulation and the cloudiness over the course of a year. Every time it turns red in this movie, there's precipitation occurring. And what you can see are these beautiful tendrils of moisture that emanate from the tropics and head down to Antarctica and periodically actually cross right over the West Antarctic ice sheet here. This is how moisture gets to Antarctica. The Pine Island Glacier area that I was just talking about is located right about here, and you can see once in a while it's getting hit by storms. Those storms are obviously, there's wind associated with this, and the wind is blowing on the ocean, and the ocean is responding to that wind. And what we've discovered, I shouldn't say we so much here, this is mostly colleagues in Britain who have done this. This is a cross-section of the area in front of Pine Island Glacier. There's the schematic of the glacier, and the colors are the temperature of the water. This is an El Nino year. This is a La Nina year. This is the same thing, but in map view. This is the flooding of the continental shelf by this warm water. basically what's happening is that when the winds are strong, it's pushing the water up against the ice sheet, and when they're weak, they're not. It's way more complex than the Earth is getting warmer and the ice is melting. That's the main message I'm trying to get across here. So all of this has to do, of course, with our future, because the melting of those ice sheets is now contributing to sea level and has the potential to contribute to sea level in the future. This is a graph from the latest Intergovernmental Panel on Climate Change report. In 2007, that community published a report in which they said our top estimate for sea level rise by 2100 is 59 centimeters, but we're not including the ice sheets because we don't really know what's going to happen. In the intervening 5 or 6 years, a lot has been learned, like what I just illustrated. And it's now actually very clear the ice sheets are contributing to sea level and will probably do more. The red curve shows what's going to happen, according to the IPCC, if we keep burning fossil fuel at the rate we're doing. The blue curve is the unrealistic one because it assumes we've done something about that. The minimum value, the minimum estimate for the red curve is about 80 centimeters. So roughly the bottom estimate is now at the maximum estimate from the last report. And this is mostly because of new understanding of how the ice sheets are responding to climate change. And I'm going to stop right there and pass the mantle on to Anna.
Thanks, Eric. And thanks also to the Whatcom Museum and in particular Barbara Matilski for organizing the Vanishing Ice exhibition and all the program. I know there was a lot of people involved in all of the programming, and I'm glad to be a part of that, and thank you all for coming today. I'm really glad Eric set me up really well because I was a bit nervous about getting into some of the science parts of the influence on my work, so I don't have to now, which is great. But I'm going to be talking to you about the project I've been working on for about the past 6 years, and I call that project Deep Ice, Deep Time. And I'm first going to just give you a little bit of the background of my work, where I got here. I think about what really motivates me at my core, and I think that I'm really interested in stories. And I love being out in nature, and I look for stories out in the land. And I think in particular, I'm looking for stories that, well, maybe not stories, but the imprint of natural processes and human processes and how it changes the way the physical and visible world looks. And what does that look like? And so for years, I had been doing some work with trees and with soil strata. And this is one of the more recent ones that I did of that show both the tree and the soil strata. And in trying to, in the prints, which are just abstract, beautiful prints, but trying to get a notion of that there might be some stories within this strata, and what are they? I'm really interested also in natural science research. I always have been. And I think it's because like me, I think they are also interested in kind of a contemplative examination of the land, looking out into the land and saying, what is it that I'm seeing? How can I understand it better? Also, I live in this glacial environment. We all live in this environment that's completely sculpted by a very large glacier. And I'm really aware of that, and I'm always very excited by when I see signs of that, and going up into the mountains and drawing glaciers. And so I've kind of, in the back of my mind, I think always was wondering about the glacier, the ice and what it was doing. But then a trip to Fairbanks in the wintertime really got me charged about ice. And who wouldn't be if you went to the ice carving festival in Fairbanks, because there was just an amazing amount of beautiful, sculptural, gorgeous ice. And I was visiting up there a couple of science friends, one of whom is also a paleoclimatologist and does similar work to Eric. And we talked a lot about isotope science and climate science, and that's really when I first learned about ice cores and that they did ice cores. And so I came back to Seattle really interested in trying to find out more about that, and was fortunate enough to track down Eric Steig, and just to give him some great kudos that he is a very creative and, I mean, beyond being just a brilliant scientist, he's also a very open-minded and creative thinker, and was really open to helping me understand this better as an artist. And so he gave me some great books to read, but also said, you know, you need to go and look at these things. As he said, I think maybe wondered, is she really going to be able to make sense of this? But I went to the National Ice Core Lab, and some of the cores from Greenland are actually quite beautiful. This is one that shows, let's see if I get this pointer right, that shows the summer and winter strata quite clearly. And so I spent hours in that lab, and also at the ISO lab at the University of Washington, where Eric had invited me in to look at some of their cores. And I just spent hours drawing the cores, and really it was an excuse to just look at them. And then, as well as Eric, I also talked to several other scientists at the University of Washington, glaciologists, who shared with me the data that they were working on. And I began a series of ice prints, or I call it the ICE series. And these are multimedia prints that use a combination of imagery, some of which from my own drawings of crevasses and glaciers, and also scientific data like ice penetrating radar, and also some strata imagery. These are some of which are very abstracted, and also just imagery of the ice cores themselves. And so here's a few of those. And these are mostly, well, they combine a micro and macro scale, but a lot of these are kind of a micro scale of the strata, oops, back up here, microstrata with some patterns of the ice as it's forming. And I also worked on a series of paintings or drawings about the Northwest glaciers. And this is when I first began to get into areas of large white spaces. And I think was very compelled to want to go see these large white spaces. And so I set about trying to write a grant to go there with the National Science Foundation program. Now, artists have been going on expeditions with scientists for hundreds of years, and really before the advent of photography, they played a really essential role in documenting a lot of the things that people were seeing. And there was this very symbiotic relationship that they had. But more recently, this is, oh, by the way, this is a piece by a lesser-known artist, George Marsden, who went with the Shackleton expedition. And then this may be in the Vanishing Ice show, but one like it by Edward Wilson, who went with Scott on his expedition. More, did I, hang on. Yes, okay. So the I'll just give you a little bit of, National Science Foundation started officially sending artists down to the ice in 1980. And it's a competitive process. You submit a grant proposal, and they send about 3 to 5 people there, and they support your travel and your stay while you're on Antarctica, and all your equipment that you need. More recently, some of the artists who've gone there are working with scientists in new and different ways. Lita Albuquerque's piece, Stellar Axis, she worked with an astronomer to come up with this celestial map, essentially a celestial map that is laid out on the McMurdo Sound, kind of an imprint of that. And I think that there's an increasing number of artists who are working with scientists in a new and different creative way, because we're no longer necessarily strictly documenting what they do. Photography's great at that. We can come up with new creative expressions. So I was really lucky in that I got selected to go. And for most people going to Antarctica, it begins with a very large plane ride. Really sets you up for being very excited to be there. And I am missing a slide, maybe? I am missing a slide, okay. Anyway, there's a couple of days in the main station, McMurdo Sound, McMurdo Station, where you learn a little bit about how to be safe on the ice. And then I headed out to West Antarctica, which I'm glad you had the maps there to show where I went, in the middle of the West Antarctic ice sheet, where it looks like this. And the arch that Eric was talking about, this is it. It's mostly buried by the snow. And it's 40 feet tall, so it's probably about this far under the snow. And it's quite a large building, and I spent most of my time in this just flat white space. It truly looks like this. That day in particular, it was overcast. It wasn't a whiteout, there wasn't any fog or anything, but the overcast light created it turned everything into a solid white. I also spent time in the arch, and this is the same photo, but just to give you my perspective of it, it was really impressive for me to go to this place. I'm thinking, you're in the middle of, essentially you feel like you're in the middle of nowhere, and yet there's this amazingly complex technology that has to go 2 miles into the ice. I mean, if you think about what it takes, there's incredible pressures at that depth to drill, to even get the ice up, and I was really impressed with the technology that was involved in that. And all of the engineers and technicians and scientists that were involved. And then the ice, again, this is gorgeous core that we both used, came over to the other side of the arch where the scientists measure it and do some measurements and also pack it and get it ready to go back up to the United States. Now, I was there, the year that I was there was when they brought up most of as Eric said, most of the ice is just plain clear. There's really not much strata visible. But when I was there was a whole section of the core that was coming up with a lot of ash layers and a lot of dust layers. And it was great that I was there during that time. People got very excited about it, to be able to see visible layers. Because at that depth, a lot of what accumulates in the ice gets so thin that it's not visible anymore. You can measure it chemically, but you can't see it. So this was really exciting. And then I also spent my time in the beautiful, beautiful snow pits. And for me, even though the scientists were there, gathering data about the density and qualities of the snow, I was just there taking in the color and the patterns and doing my own little sketches of those. And then spending a lot of time in this white space. But there was something that was really interesting that I was wondering if this would happen, and it was amazing to actually watch it happen to me, which was when I first got there, just as you're seeing here, it's just white. It's just, what is there? What am I ever going to do? I mean, really, here's the white piece of paper. But after about a week, our brains are amazing, and we want to see pattern, we want to see detail. And so with the lack of information coming in, my brain began to seek out a finer and finer grade of detail. And what once seemed like just plain white, I began to realize that in fact this place was ever changing. The sky, the light that would come through some of the clouds was always changing. It would sometimes be yellow, sometimes be purple. Sometimes it would actually be sunny occasionally, and you could see a lot of details in the snow. And it was actually quite a dynamic environment. I mean, I would set up to draw, and inevitably within a half an hour to an hour, it would be a different scene. And so I came back with all of that experience and set about making a series of large white paintings with details. This one, my main goals in these paintings were to, first of all, just try to capture a sense of the scale and our imprint on this place. So here's this large white expanse of snow with the arch that is very much there, but it's really a very small part of this place. And again, the ice runway with a twin otter plane landing, it would come and go. And then this one with the, I must be on hang on a second, oops. I would ski away from the camp, and then I could really get a perspective of just how small our imprint was on this very large space. And this is the camp in the distance in my ski tracks. And then I also did a series of small etchings that were really just little stories of the place. And I'm sorry, I'm having a technical difficulty in that it's switching. It's going to a slideshow mode.
Doing it itself?
Yeah, I think so. Now it's stopping. Hang on, maybe I'm hovering over it and it's, okay, yeah, get my hand away. So these just show what the camp looked like. I mean, you know, there's the snow and then there's all the equipment that's on it, and it's just really a way of kind of telling a story. And then I continued the ice series, and these began to get bigger. I still was working with this micro scale of an ice core and some of the melt layers in this particular piece, but also the larger macro scale of the ice sheet itself, and kind of an abstracted idea of, yeah, I keep hitting this, an abstracted idea of the ice core going down into the ice sheet. And then similar to the one here at Vanishing Ice, some of these are combining the two, micro and macro. Yeah, it's happening again. Okay. And I'm really glad Eric explained a little bit about Pine Island Glacier and the edges and how dynamic they are, because being up on the ice sheet, it was an incredibly stable place. You know, standing in the middle of the ice sheet, it seemed like it went on forever. It was not changing at all. And yet, in fact, the edges of the West Antarctic ice sheet are very much changing and very dynamic. And so I really wanted to create a series of prints that alluded to that. And so this is one that is just getting at the Pine Island Basin. And then some of these paintings that were similar to the West Antarctic, or the Waste Divide paintings, that combine the stability of this large ice sheet with the breakup of the edge, or the collapse, essentially, of the edges. And so these are sort of abstracted. And this one is, again, a large chunk of a ice shelf collapsing. So that same year, I was invited with Eric and his colleague here at Western Washington University, Doug Clark, and they are doing some research about North Pacific and trying to better understand the climate in the North Pacific. And so they were drilling an ice core up on Mount Waddington, which is in British Columbia. And I was invited to come up to see that and be in that environment. And it was a wonderful opportunity because this is a much less complex ice core, mostly because it's a much shallower ice core. They were drilling only a couple of 100 meters. But it gave me an opportunity to see in kind of a better detail, because it was more or less complex. It allowed me to really understand the operation and what they were doing. And so this is the drill, and me trying to draw out there. Fortunately, I was there during a very beautiful time. It was very stormy there that year. I was lucky. And then I came back and did a series of these drawings and paintings that were also trying to kind of put the context of our being there into the larger space of this environment. And also some smaller detailed etchings of the camp and what that was like, and the journey up there, what that was like. And so this was a suite of etchings that I did about a year ago to this year. And then, you know, ever since, so now I really wanted to talk about the most recent project that I've been working on that's ongoing right now. And it really began several years ago. I've been wanting to, as I said earlier, I've been really struggling to try and communicate a sense of the scale of these projects. I mean, to talk about 3,500 meters of ice or 2 miles of ice. What is that? I mean, we can, I walk 2 miles, I understand that, but to actually lay out 2 miles of ice end to end, my brain can't really conceive of that. And so I was trying to come up with some kind of art project that would at least allude to that or grapple with that. And so largely because of my background, and I've studied medieval history, and so I was aware of reliquaries in history, and so I came up with this idea of creating reliquaries for both of the ice core projects. The reliquaries are, if you don't know, they're various cultures have created them over time. With Middle Ages and Christianity, they would put parts of saints and other important people into little containers and contain them in these boxes that were then worshipped, and they were very sacred objects. And I was feeling that the water from these ice cores, that there is a sacredness to them. They offer us a lot of wisdom. And while I don't necessarily think of them as religious objects, I do think of them as very special and important things. And so I created these ampules from lab glass. And again, Eric Steig was very generous in allowing me to come into the ISO lab and create these and also access the samples from the water to put, then I put in each of these, I put a small amount of water from each meter of the core. And then I began with the Mount Waddington core because of its smaller scale. It would be a much less complex piece to try to work out first. And so the ampules, the part of Mount Waddington essentially is the box, the reliquary itself with the ampules in it. And then it is surrounded by 142 silk organza tubes that have print of each meter of the core. Because one of the things the scientists do is they take high-resolution scans of each core, and so I got those and printed them onto these and made these tubes that then surround the reliquary and create a contemplative space to just be with and have wonder about, try to convey my wonder about this beautiful science. And then I also collaborated with sound artist Steve Peters, who made an 8-channel audio piece that was taken from field recordings of the glacier melting up on Mount Baker. And that was going on in the space, and it made for, if you were lucky enough to get in there with nobody else in there, it made for a really lovely visit. And this was up just, unfortunately, just last month. I wish it was still there, at Francine Setter's gallery. And then in the over last year, I've been tackling the waste divide. The waste reliquary is, as I said, 3,405 meters. So I first had to make all of these ampules, fill them, go into the lab. That took many, many months. And then they're being sewn onto these panels. These are silk panels that are dyed different colors that correspond to the different parts of the ice core. And then they're hung at a level that corresponds to the isotope signature, and that again is a proxy for temperature. And so when it's completed, out here, and here is a detail of them, each one of these is numbered with the water and then sewn onto these panels. And in its entirety, it'll be about a 22-foot long piece, and it will create a graph of the temperature record for the last 68,000 years of West Antarctica in kind of an abstract installation piece. Look for it someday soon. Then finally, in continuing this work, I'm really been, this is, working with the scientists and going into these landscapes has just been a profound experience for me, and it has definitely altered the course of my work. And I was fortunate enough to be invited along again with Doug Clark and Eric Steig's team to go up to another ice field up in British Columbia this summer. And so, and when I went up there, I realized that it really completed the story for me, because I began, and it's kind of in reverse, because I began by looking at ice cores. I then went to a place where they were drilling an ice core, and now I got to go to a place where they were looking at a spot to think about where they might drill an ice core. And some of the science they do to do that is they take GPS measurements to get a sense of the glacier, whether it's moving, and maybe what direction it's moving in. And also ground penetrating radar to try and get an idea of the depth and what the bed looks like. And these guys are out there. They were amazingly strong scientists out there with equipment that they had to set up in the field in very difficult conditions and dragging it around on the ice sheet to get some data. And then also they dug some snow pits, and I thought this was a different view of the snow pits. And here's two of them here from the air. And I got to be there to just take it all in, do some drawings, and try and get a sense of this beautiful landscape. And so hope to work on that work in the near future. So with that, I just want to thank. There's a bunch of people to thank over the years of this project, but in particular, there's some folks that really stand out who have been incredibly supportive, and in particular today, Whatcom Museum and Chris Brewer and Barbara Matilsky, and also the North Cascades Institute. So thank you all for coming, and I think we'll take questions.
We'd like to take a few moments now for you to ask questions of either Dr. Steig or of Anna McKee.
Hello, thank you for such a wonderful program. And I wanted to ask you, having toured the North Cascades and seen the extraordinary glacial blue, and been awed by that and wondered how to recreate it, you've done a wonderful job with the silk, which I think was so beautiful and such a great representation of that kind of ethereal, strange color. How long did it take you to come up with that as the medium for your displays?
Good question. I think you know, the color has been the most challenging part, because you really can't recreate it. It's light. And I mean, I look at people like James Turrell, and I mean, they're the guys who are really doing that work in incredible ways. But I thought that the silk, I actually have a background in fabric. I studied fiber art as an undergraduate. So it's funny how long it took me to sort of go, oh, you know, the organza actually is quite great. It didn't seem initially like a very good idea. I was trying to work with glass and even how can I get this ice actually and exhibit that. But I eventually realized that the organza, it's stiff and it dyes beautifully. And the dyes, because again, it's allowing light to come through, it better evokes, I think, the qualities of the ice colors. And I think it was a couple of years ago I realized, oh, duh. And it also has these other qualities of being, I mean, the ice it's really hard and cold, and it seems, and yet it's incredibly fragile. And so the organza has that sort of ephemeral quality that was kind of a different metaphor for it. So thank you.
Excuse me. How long do you think that it will take for the United States to recognize global warming, climate change? And since most of the world has signed the Kyoto Treaty, I'm just wondering whether it'll be 5, 10, or 20.
You know, I don't have an answer to that in terms of time, but I think something that maybe isn't widely appreciated is that, like in many things, the people, as represented by their government, are way behind where the people who are actually sort of on the ground doing things are. Corporations, including ExxonMobil, there's no debate about this in those communities. I was at a meeting in Iceland recently, and there was this sort of shocking moment. There was 5 people up on stage, all from oil companies, and they were talking about all this oil exploration that they were going to do in the Arctic. And a young woman came up in the question and answer session, and she basically said, how can you do this? How can you be talking about drilling there when you know that the reason it's melting and allowing you to drill there is because of all the fossil fuels you're burning? And the guy said, implement a carbon tax. I mean, this was the oil company guy saying, stop yelling at us. You know, it's clear what's happening. I'm not going to debate with you that it's happening. But somebody's going to go and drill that oil, and the only way to change that is to change the demand. I was amazed to hear a corporate person saying this. Now, of course, the same corporation may be doing things to counter exactly that policy, but nevertheless, I don't think it's a matter of information. I think it's a matter of political will in the face of all these other political and economic pressures that occur. I sometimes wonder, you know, I go out and talk about this stuff. I'm not so sure it's actually that important, other than sort of keeping up people's memory that, yeah, we actually know this, but I don't feel there's an educational problem. I think there's a political problem. What to do about it, I don't know.
I was thinking about trying to educate young people, and I was wondering if either one of you have seen the Happy Feet movies, and if you might comment on them.
Have you haven't seen them? Okay, I guess this is to me. I've only seen one of them. I guess, I mean, I liked it. My kids liked it. They didn't talk, they were quite apolitical. They talked about something else, right? Like they sort of made up this story about overfishing or something, which of course is not particularly the issue in Antarctica. Maybe it's an issue, but it's not the big one. So I think one could do better than those movies, I think is what I'd say.
I was curious about the sort of much higher temperatures in the past 10,000 years in the Holocene. Are there theories and this has nothing to do with the current amount of carbon, you know, and climate change, but I'm just curious about, do we have ideas about why that happened in the last 10,000 years?
Yeah, so actually something you may remember from those graphs, I won't flip back to them, but over the last 10,000 years in both hemispheres, south and north, the average trend has been of cooling. And we've actually known since about 1911 or so, when it was predicted that would be what we'd find when we had more data, that this has to do with the wobble of the Earth around the sun. The tilt of the Earth is sometimes greater. And when it's very great, which it was about 10,000 years ago, it was at a maximum angle, about 24 degrees, as opposed to about 23.5 that it is now. Summers are warmer because you're pointing more at the sun, and winters are correspondingly colder. But at the high latitudes, winter's dark anyway, so it doesn't make any difference. So the dominant thing is the summers are warmer, and that entirely explains that trend. But I should add that one of the many great discoveries from ice cores is the proof of that theory that was devised actually back in the late 1800s, that this would be the cyclicity of ice, of climate through time.